OCR Physics, and this is my first thermal physics video, and it's about gases and temperature. So there is a fixed mass of gas in this balloon. Okay, the mass of gas isn't going to change, and these are the properties that I am interested in that we're going to be using in this video. So you've got the mass of the gas, capital M, and that's in kilograms. You've got the pressure, little p, newtons per meter squared or Pascal, either of them is okay. The volume, big V in meters cubed, the temperature, big T, degrees centigrade or Kelvin. We're going to talk a lot about Kelvin, and eventually we're going to be using Kelvin all the time. So temperature, I'm going to use little m for the mass of a particle. So little m is the mass of a particle, big M is the mass of the gas. Pressure, it's worth remembering that atmospheric pressure is about 100 kilopascal. 1 atmosphere is very close to 100 kilopascal, 1 times 10 to the 5 Pascal. Volume shouldn't be a problem, but worth remembering that a centimeter cubed or a milliliter is a millionth of a meter cubed. Yeah, there's 1,000,000 centimeters cubed in a meter cubed. And a litre is 1,000th of a meter cubed, so 1 times 10 to the minus 3. You probably won't need them, but I have seen sneaky little questions where you need to figure that out. Temperature, as I said, I'm going to talk a lot about the Kelvin scale later in the video. And then finally, little n is the number of moles. Big N is going to be the number of particles, and 1 mole is Na particles, and Na, you should know, is Avogadro's constant, which is 6.02 times 10 to the 23. The gas laws. Now, the gas laws are all about the relationships between pressure, volume, and temperature. So you've got pressure and temperature at constant volume. Now, volume and temperature for OCR, we don't need to know this. It's called Charles' law. And then pressure and volume, very important at constant temperature. So pressure and temperature, which is called the pressure law. Volume and temperature, not bothered. Pressure and volume, very important. That's Boyle's law. So first of all, the pressure of a gas is proportional to its temperature. If you put this glass bulb called a jolly bulb in a water bath and you measure the pressure of the gas, so its volume can't change, its volume is fixed, and you're measuring the temperature and you heat it up and you plot a graph of pressure against temperature, you get a straight line. And that is the pressure law. Now, if you extrapolate, if you carry the straight line down, 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 down till it cuts the axis, there's this idea that there might be a temperature at which this gas would have no pressure. Now, in practice, that's not going to happen, because what will happen to a real gas is that it will liquefy and then it will probably turn into a solid, and other things would be happening at very, very low temperatures. But there's this idea that if it stayed as a gas, then there is maybe the coldest possible temperature, which would be absolute zero. And if you do this experiment, which you should, if you do it well, then you get a value of minus 273 degrees centigrade. And that's maybe the coldest possible temperature, or absolute zero. Pressure and volume, you should know this apparatus. Basically, we have this gas in a tube, a fixed mass of gas. There it is in that glass tube. It has a particular volume that you can measure, and then you pump it up, you make the pressure bigger, and the oil in the bottom squishes the gas, so the pressure and the volume changes. When the pressure gets bigger, the volume gets smaller. You're supposed to leave it a while between readings to let the temperature kind of go back to where it was to begin with. And basically, pressure against volume you get something that looks like an inverse relationship. And so to test that, you plot pressure against 1 over volume and you get a straight line. And so we get Boyle's law. And Boyle's law says the pressure of a gas is inversely proportional to its volume at constant temperature. So Boyle's law says that the pressure of a gas, P, is proportional to 1 over V, or another way of saying that is that pressure times volume equals a constant. Okay, so pressure times volume equals a constant, and that is Boyle's law, and that's at constant temperature. There are 2 types of gas. There are real gases. Real gases, the air in the room that you're in is a real gas, okay? And real gases obey Boyle's law pretty well most of the time, okay? At extremes of pressure, very high pressures, very high temperatures, and very cold as well, then they start to deviate a little bit, okay, or a lot. But real gases obeys Boyle's law most of the time. Then there's this thing called an ideal gas, and an ideal gas is an imaginary gas that obeys Boyle's law all of the time, at any temperature. And learn that an ideal gas is an imaginary gas that obeys Boyle's law all the time. Let's talk about temperature. What do we mean by temperature? Temperature is how hot something is. It's the degree of hotness. Now, the problem with that definition is that it's very subjective. You know, these people up there who are living somewhere near the North Pole, oh, what a lovely warm day it is today. And then this guy in the middle of the desert, oh, it's a bit chilly today. Yeah, temperature, degree of hotness is very subjective. It depends on the observer. What we need is an objective temperature scale, an objective way of defining temperature. And many attempts have been made to devise a temperature scale based on the property of a substance. For example, the pressure of a gas. So what you need is you need a substance that has a property that varies with temperature. For example, it might be the pressure of a gas, it might be the volume of a gas, it might be the resistance of a wire, and there's loads of other things that vary with temperature, okay? Maybe the resistance of a thermistor, lots of different things. You also need 2 fixed points. Now, a fixed point is basically something that always happens at the same temperature. And you can call one of the temperatures 0 and you can call the other one 100. Unless it's somewhat weird like Fahrenheit, you know, call one of them 0 and call one of them 100. For example, the temperature of melting ice, let's call that 0. The temperature of boiling water, let's call that 100. And then what we do is we assume that there is a linear relationship between this property and the temperature between and beyond these points. So, for example, I get my jolly bulb and I put it in melting ice, and then on the pressure gauge I mark 0, and then I put it in boiling water, and on the pressure gauge I mark 100, and then I get a pen and I divvy it up from 0 to 100. Okay, so I assume that there is a linear relationship between 0 and 100. Problem with that is that all of the different thermometers based on different things, they will all agree at the fixed points at 0 and 100, but they don't necessarily agree between 0 and 100. Now, why? Because all of them make this assumption that there is a linear relationship, but there's no way that you can test that relationship because you would need a thermometer to do it. So you need a thermometer to test a thermometer. What we need is a universal temperature scale. You know, everybody needs to be using the same property. So Lord Kelvin, who before he became a lord was William Thomson, but then he became Lord Kelvin, devised a temperature scale that was actually based on an ideal gas. And it's the Kelvin scale or the ideal gas scale. And basically his quantity that varies linearly with temperature is PV. So you make the assumption that PV is proportional to temperature. This was sensible because all of the pressure and the volume thermometers tended to agree with each other. And also this expression is actually just a combination of the gas laws. I know we haven't done the volume law, but the volume law basically says that V is proportional to T. So it's a combination of the gas laws, and it's based on thermometers that agreed with each other. But then the two fixed points are absolute zero, which is the temperature at which the pressure of a gas is zero, which is 0 Kelvin, capital K Kelvin, which is minus 273 degrees centigrade. It's actually 0.15, but don't worry. And the melting point of ice, which is 273 Kelvin or 0 degrees centigrade. You don't need to know about the triple point, by the way. If you do chemistry, you'll know what the triple point is. Don't worry about it. I regret mentioning it now. Okay, so we have PV is proportional to T, and we can do an experiment to actually get a value for the gas constant. If we assume in our experiment that the gas is behaving as an ideal gas, okay, and what we get is for 1 mole of an ideal gas, PV equals RT, capital R, and capital R is called the gas constant. And it's equal to 8.314 joules per mole per Kelvin. Okay, that's for 1 mole. If you do it for n moles of an ideal gas, we get PV equals nRT, and that's called the equation of state for an ideal gas. And it's a very important equation, PV equals nRT. The equation of state, because if you know the pressure and volume and temperature of a gas, we say that we know what state it's in. Yes? And that's the equation of state for an ideal gas. Here's a little question for you to have a go at. Pause the video, pen, paper, calculator. I'll show you the answer in 3, 2, 1. There you go. Hopefully you will have changed your degrees centigrade to Kelvin. Okay, from now on we are using Kelvin. So PV equals nRT. A useful form of this equation is that P over T equals a constant if the volume is constant. So if you rearrange the equation, if the volume is constant, then the number of moles in the gas constant doesn't change. So P over T is a constant. You can write that as P1 over T1 equals P2 over T2. If the volume wasn't constant, it would be P1 V1 over T1 equals P2 V2 over T2. But you don't do that. You just do constant volume. So have a go at that question there. And the answer is in 3, 2, 1. There you go. Again, be careful with the temperature. Now, another constant, a very useful little constant, is Boltzmann's constant, little k. Seem to use little k for quite a few different things, but here, little k is Boltzmann's constant, and it's basically a combination of two others. It's the gas constant divided by Avogadro's constant. So if you want to check for yourself the value for little k, if you like, the gas constant is for a mole and Boltzmann's constant is for a single particle. But anyway, this is Boltzmann's constant. And so if we see that big N is the number of particles, which is little n times Avogadro's, and then if you substitute that into PV equals nRT, we get this other equation here, PV equals big N KT. So we've got PV equals nRT and PV equals N big N KT. Quite a few questions where they ask you to work out the number of particles, and you would go for this equation here. Here's a sum for you to do. Don't be lazy. Pen, paper, calculator, pause the video, get it done. And that's the answer. Finishing off the video now, something called thermal equilibrium we need to understand. What does that mean? Well, this apple is in thermal equilibrium with its surroundings. It's absorbing heat, it is giving off heat, but there is no net flow of heat. So the amount of internal energy isn't getting bigger or smaller. So its temperature is constant. There is no net flow of heat. These two objects will not be in thermal equilibrium. The hot cup of coffee, it's a higher temperature than its surroundings, so it will lose heat to its surroundings. There will be a net flow of heat. The ice lolly is colder than its surroundings, so there will be a net flow of heat inwards. Yeah, its internal energy will increase. Okay, so thermal equilibrium is when there is no net flow of heat between an object and its surroundings, and its temperature will be constant.